The Sun is 93 million miles from Earth. Light travels at 186,282 miles per second. This means sunlight takes exactly 8 minutes and 20 seconds to reach us. If the sun suddenly went dark right now, we wouldn't know it yet. For 8 minutes and 20 seconds, life would continue exactly as normal. People would go about their daily routines. Plants would photosynthesize. Solar panels would generate electricity. The warmth on your face would feel real, even though its source had already vanished. This delay exists because nothing travels faster than light. Not information, not gravity waves, nothing. The sun could explode, disappear, or transform into something else entirely, and we would remain blissfully unaware for those crucial 8 minutes. During this brief window, Earth would still receive approximately 1,361 watts of solar energy per square meter at the top of the atmosphere. The photons hitting Earth would be the last ones to ever make the journey from our star. They left the sun's surface before the darkness began, racing across space at the ultimate speed limit of the universe. Consider what you might be doing in any random 8-minute period: making coffee, driving to work, having a conversation, reading this very text. That's how long humanity would have left of normalcy, though no one would know to cherish it. The strangest part is that different planets would find out at different times. Mercury would know first, after just 3 minutes. Venus would learn at 6 minutes. Mars wouldn't know for 12.5 minutes. Jupiter would remain in normal sunlight for 43 minutes after the sun went dark. The news would ripple outward through the solar system at light speed, a wave of darkness expanding from the center. Weather satellites would continue recording normal solar radiation. Astronomers studying the sun would see nothing unusual. Radio communications would function normally. Every instrument we have for measuring solar output would show standard readings. The data would be real, but it would all be 8 minutes out of date. This cosmic delay means that at any given moment, we're not seeing the sun as it is, but as it was 8 minutes ago. We live our entire lives slightly in the past, at least regarding our star. Every sunrise you've ever seen actually happened 8 minutes before you witnessed it. Every sunset had already occurred when its light reached your eyes. The 8-minute delay would end suddenly and simultaneously for everyone on Earth's day side. There would be no gradual dimming like an eclipse. One moment, the sun would be there. The next, it would be gone. The blue sky would turn black instantly, revealing stars in the middle of the day. The temperature wouldn't drop immediately. Heat travels slower than light, but the visual change would be instant and terrifying. Those on Earth's night side wouldn't see the change directly, but they would notice the moon disappear. The moon doesn't generate its own light. It only reflects the sun's. 8 minutes after the sun went dark, the moon would vanish from the night sky, taking with it the gentle illumination humans have relied on for millions of years. In those final 8 minutes of ignorance, children would play outside, farmers would tend their fields, and solar panels would generate their last watts of power. It would be the final chapter of life as we know it. And no one would even know to say goodbye. When the darkness arrives, it wouldn't look like any sunset humanity has ever witnessed. There would be no golden hour, no gradual transition through orange and pink to deep purple. The sun would simply vanish, as if someone had switched off a light bulb 93 million miles away. For those experiencing daytime, the transformation would be incomprehensible. The sun, a disk that has dominated our sky for billions of years, would disappear between one heartbeat and the next. The bright blue atmosphere, scattered with sunlight, would turn black instantly. Stars would appear in what had been broad daylight, but not the familiar stars of night. These would be the stars normally hidden by the sun's glare, visible now in their true positions. The horizon wouldn't glow with twilight colors. Those beautiful sunset hues come from sunlight scattering through atmospheric particles at low angles. Without sunlight, there would be no scattering, no color, just an abrupt transition from day to night, unlike anything in human experience. For people on the night side of Earth, the first sign would be the moon's disappearance. Since moonlight is reflected sunlight, the moon would go dark 8 minutes after the sun. It wouldn't fade gradually. It would vanish as if deleted from the sky. The stars would suddenly appear brighter without the moon's competing light, but the familiar lunar disk would be gone, leaving only a suspicious dark circle where stars should be. Cities would react with automatic systems first. Streetlights equipped with photosensors would switch on, confused by the sudden darkness. Buildings with smart lighting would illuminate. Car headlights would activate automatically. In the span of seconds, every artificial light source designed to respond to darkness would spring to life, creating scattered points of light across the darkened landscape. The psychological impact would be immediate and severe. Humans have an instinctive fear of darkness rooted in millions of years of evolution. But this wouldn't be ordinary darkness. Night is supposed to follow day gradually, predictably. This sudden plunge into blackness would trigger primal panic responses. People outdoors would likely freeze in place initially, unable to process what their eyes were telling them. Air traffic control would face instant crisis. Pilots flying in clear daylight would suddenly find themselves in complete darkness. While commercial aircraft are equipped for night flying, the sudden transition would be disorienting and dangerous. Airports would need to switch immediately to night operations, activating runway lights and updating approach procedures without warning. Communication systems would explode with activity. Emergency calls would flood dispatch centers. Social media would surge with posts from the day side of Earth, while the night side would wonder why the moon had vanished. News organizations would struggle to explain something that shouldn't be possible according to physics. The temperature wouldn't change immediately. Earth's surface and atmosphere retain heat, releasing it slowly. For the first few minutes, maybe even an hour, the temperature would feel normal. This disconnect between the darkness and the warmth would make the situation even more surreal. It would feel like standing in a pitch-black room that somehow remained warm and comfortable. Animals would react with confusion and distress. Birds would return to their roosts, thinking night had fallen. Nocturnal animals would emerge, confused by the sudden darkness but still sensing wrong timing through other cues. Flowers that close at night would begin folding their petals. The natural world would attempt to follow its programmed responses to darkness, but nothing would quite fit. Within minutes, humanity would realize this wasn't an eclipse or any known astronomical phenomenon. The sun hadn't been blocked. It had gone out. Before we go further into this thought experiment, we need to establish why the sun suddenly going dark is physically impossible. Understanding this helps us set proper boundaries for our scenario, while appreciating the stable physics that actually govern our star. The sun is not a light bulb that can be switched off. It's a massive nuclear fusion reactor, converting 600 million tons of hydrogen into helium every single second. This process releases energy equivalent to billions of nuclear bombs detonating continuously. The fusion occurs because the sun's enormous mass, 333,000 times Earth's, creates pressures and temperatures in its core that force hydrogen atoms to merge. For the sun to suddenly stop shining, fusion would need to cease instantly throughout a core spanning 200,000 miles. The temperature there is 27 million degrees Fahrenheit. The pressure is 250 billion times Earth's atmospheric pressure. These conditions took millions of years to establish as the sun formed from a collapsing gas cloud. They can't simply vanish. Even if fusion somehow stopped instantly, the sun would still glow for thousands of years. The energy generated in the core takes between 10,000 and 170,000 years to reach the surface, bouncing between atoms in a random walk through dense solar material. The sun we see today is shining with energy created when humans were still developing agriculture. That stored energy wouldn't disappear just because fusion stopped. The sun's gravity also prevents sudden darkness. If fusion stopped naturally, gravity would cause the core to collapse, actually increasing temperature and pressure until fusion restarted. This balance between gravity pulling inward and fusion energy pushing outward has maintained itself for 4.6 billion years. It's a self-regulating system that resists sudden changes. For our thought experiment, we must invoke impossible physics. We're imagining the sun's light and heat simply ceasing, while its mass remains to keep planets in orbit. This couldn't happen through any known physical process. No weapon could do it. No natural phenomenon could cause it. We're essentially imagining magic for the sake of exploring Earth's dependence on solar energy. This scenario differs from the sun actually disappearing. If the sun's mass vanished, Earth would fly off into space in a straight line, following Newton's first law of motion. We'd become a rogue planet, drifting through interstellar space. By keeping the sun's gravitational mass, but removing its electromagnetic radiation, we can explore temperature and ecosystem effects while maintaining orbital mechanics. We're also assuming the shutoff is instant and complete. No visible light, no infrared radiation, no ultraviolet, no radio waves, nothing. The entire electromagnetic spectrum from the sun ceases. This is crucial because even a tiny fraction of normal solar output would dramatically change our scenario's timeline. It's worth noting that stars can vary in brightness. Variable stars pulsate, changing luminosity over periods of days to years. Some stars experience sudden dimming when planets or dust clouds pass in front of them. But no star has ever been observed to simply turn off. Even dying stars take thousands of years to fade. Supernovas, stellar explosions, actually increase brightness before the star disappears. The closest real phenomenon to our scenario would be a thick dust cloud passing between Earth and the sun. But even the densest interstellar clouds aren't completely opaque. Some radiation would get through, and such a cloud would take decades to fully engulf the solar system, not seconds. By acknowledging these impossibilities up front, we can focus on the thought experiment's real purpose, understanding how fundamentally life on Earth depends on the constant energy streaming from our star, and what would happen to our planet if that energy suddenly stopped. Even with the sun's light extinguished, gravity would continue its eternal pull. This is crucial to understand. Mass and electromagnetic radiation are separate phenomena. The sun could go completely dark, while its 1.989 times 10 to the 30 kilograms of matter remained in place, holding the solar system together through gravitational force. Earth would continue orbiting at 67,000 miles per hour along its elliptical path. We wouldn't drift into space or spiral toward the darkened sun. The laws of orbital mechanics don't require light, only mass. Every planet, asteroid, and comet would maintain their celestial choreography in perfect darkness, like dancers following memorized steps on a pitch-black stage. This gravitational continuity would create strange juxtapositions. The Moon would still orbit Earth every 27.3 days, pulling our oceans into tides twice daily. But the Moon itself would be invisible, a dark mass moving through dark space, revealed only when it occluded background stars. High tide would arrive on schedule in complete darkness, waves pulled by an invisible force toward an invisible satellite. Jupiter's 4 largest moons, Io, Europa, Ganymede, and Callisto, would continue their orbits undisturbed. Saturn's rings would maintain their structure, held in place by the planet's gravity, though no sunlight would make them shine. Every moon in the solar system would keep circling its parent planet, following paths established billions of years ago, needing no light to guide them. The asteroid belt would persist unchanged, millions of rocky bodies continuing their slow orbits between Mars and Jupiter. Comets would still follow their elongated paths, though without solar heating, they wouldn't develop the spectacular tails we associate with them. Halley's Comet would return on schedule in 2061, but it would pass by as a dark, frozen nucleus, invisible to Earthbound observers. Space missions would face interesting challenges. Spacecraft navigate using star trackers and sun sensors. With the sun dark, they'd lose a primary reference point. However, probes like Voyager 1 and 2, already in interstellar space, wouldn't notice much difference. They long ago stopped relying on solar power, running on radioisotope thermoelectric generators. They'd continue their journey out of the solar system, carrying golden records that would outlast the darkened Earth they left behind. The International Space Station would maintain its orbit 250 miles above Earth. Without atmospheric drag, which would still exist initially, it could circle our planet for years. However, its solar panels would become useless decorations, forcing immediate reliance on battery power. The station would have mere hours before life support systems failed, unless cosmonauts could somehow generate power through other means. Satellites would continue orbiting according to their programmed trajectories. GPS satellites at 12,550 miles altitude would maintain perfect positioning, though the civilization relying on them would be collapsing below. Communication satellites in geostationary orbit would hover over their assigned longitudes, faithfully relaying signals for as long as their batteries lasted. Weather satellites would continue circling, recording the death of Earth's climate system in precise detail until their power failed. Earth's rotation wouldn't change. We'd still have 24-hour days, though distinguishing day from night would become meaningless without the sun. The planet would continue spinning at 1,000 miles per hour at the equator, creating the Coriolis effect that influences wind patterns, at least while temperature differences still existed to drive winds. Even Earth's axial tilt would remain at 23.5 degrees, though seasons would become irrelevant without solar heating. The North Pole would still point toward Polaris. The celestial mechanics that have governed our planet for billions of years would continue perfectly, a clockwork universe operating in absolute darkness, proving that gravity needs no light to maintain its invisible grip on the cosmos. Earth's surface temperature averages 59 degrees Fahrenheit, 15 degrees Celsius, thanks to a delicate balance. The Sun delivers 173,000 terawatts of power continuously, while Earth radiates heat back to space as infrared radiation. Without incoming solar energy, only the outgoing radiation would remain, beginning an inexorable cooling that would transform our world. The cooling wouldn't be uniform. Different materials lose heat at different rates through radiation, conduction, and convection. Deserts, which can swing from scorching days to freezing nights, even with the sun, would plummet fastest. The Sahara could drop 50 degrees Fahrenheit within the first 12 hours. Rocky surfaces radiate heat efficiently into space, lacking the thermal mass to maintain temperature. Oceans would cool much more slowly. Water has enormous heat capacity. It takes significant energy to change its temperature. The top few meters of ocean contain as much heat as the entire atmosphere. This thermal reservoir would become humanity's temporary buffer against the cosmic cold, releasing warmth that took decades to accumulate. Cities would create microclimates of retained heat. Concrete and asphalt, the urban heat island materials that make cities hotter than surrounding areas, would now work in reverse. Buildings would radiate their stored warmth, creating slightly warmer pockets. Underground infrastructure, subways, sewers, utility tunnels, would remain warmer longer, insulated by earth and concrete above. The atmosphere itself would cool from the top down. The stratosphere, already cold at -60 degrees Fahrenheit, would drop toward absolute zero within days. The troposphere, where weather occurs, would cool more slowly, held slightly warmer by heat rising from the surface. But without temperature differences to drive convection, the normal mixing of atmospheric layers would cease. Cloud formation would change dramatically. Clouds form when water vapor condenses around particles in the air. In the first hours of darkness, residual heat would still evaporate some water, potentially creating low clouds that would trap a bit of remaining warmth. But as temperatures dropped, all atmospheric moisture would begin freezing and falling as snow or ice crystals, clearing the skies permanently. Within 24 hours, average global surface temperature would drop below 32 degrees Fahrenheit, 0 degrees Celsius. This is just an average. Polar regions would be far colder, while tropical oceans might remain slightly above freezing. The last rain would fall during this period, quickly transitioning to snow as temperatures plummeted. Every raindrop would be a small farewell to the water cycle that sustained life for billions of years. By the end of the first week, average surface temperature would reach 0 degrees Fahrenheit, minus 18 degrees Celsius. This is colder than Antarctica's winter average. Rivers would freeze solid except where flowing rapidly. Lakes would develop thick ice covers. Even the ocean surface would begin forming ice, starting at the poles and spreading toward the equator. Plant tissues would freeze and rupture. Ice crystals forming inside cells would pierce cell walls, destroying the delicate structures that enable life. Trees would crack loudly as sap froze and expanded. Agricultural areas would become graveyards of frozen crops. The last photosynthesis would have occurred days ago, but now even the physical structures of plants would succumb to the cold. Animals would cluster around any remaining heat sources. Volcanic regions would become oases, their geothermal energy suddenly precious beyond measure. Hot springs that were tourist curiosities would become survival sites. Yellowstone's geysers would continue erupting on schedule, sending steam into the frigid darkness, beacons of Earth's internal heat. Interestingly, the lack of sunlight would initially make the cold more bearable for humans than the temperature alone suggests. Wind chill requires wind, and winds are driven by temperature differences. As Earth cooled uniformly, winds would die down, eliminating the brutal wind chill that makes polar regions so dangerous. The still, cold darkness would be survivable with proper clothing and shelter, at least temporarily. Humanity has organized civilization around the rhythm of day and night for thousands of years. Work begins with sunrise, ends with sunset. Our biology expects light and dark to alternate every 24 hours. The sudden loss of this fundamental cycle would shatter both practical systems and psychological stability. Electric lights would immediately become humanity's artificial sun, but the power grid wasn't designed for continuous universal demand. Streetlights, usually off during daytime, would run constantly. Every home would need lights on 24 hours. Office buildings that power down at night would remain fully lit. The load on electrical systems would double or triple instantly. Circadian rhythms, our biological clocks evolved over millions of years, would fall into chaos. The pineal gland produces melatonin in response to darkness, making us sleepy. Without light periods to suppress melatonin, people would experience constant drowsiness. The suprachiasmatic nucleus in the brain, which coordinates daily biological cycles, would receive conflicting signals, eternal darkness suggesting sleep, while survival demanded wakefulness. Sleep patterns would fragment within days. Some people would attempt to maintain normal schedules using artificial light, but without the sun's powerful Zeitgeber time-giver signal, synchronization would fail. Families might drift onto completely different sleep cycles. Society's shared schedule, the foundation of cooperation and commerce, would dissolve. Meetings, school hours, work shifts, all would become arbitrary in eternal darkness. Mental health impacts would be severe and immediate. Seasonal affective disorder affects millions during winter months. This would be winter without end. Depression rates would soar. Anxiety would become universal. The primitive parts of our brain, evolved when darkness meant predator danger, would remain constantly activated. Stress hormones would flood our systems continuously. Children would suffer particularly. Young minds need light exposure for proper development. Vitamin D deficiency would begin immediately. Our skin produces this essential vitamin when exposed to ultraviolet light. Rickets, conquered in developed nations, would return. Growth patterns would distort. The psychological trauma of eternal darkness on developing minds would create a generation marked by this cosmic catastrophe. Navigation would require complete reimagining. We unconsciously use the sun's position for direction, even in cities. North, south, east, west become meaningless without sunrise and sunset to anchor them. GPS would still function initially, but people would lose intuitive spatial orientation. The simple act of pointing toward home would become difficult without celestial references. Social conventions around time would collapse. See you tomorrow loses meaning when tomorrow never visibly arrives. Morning coffee, lunch breaks, dinner time. All these temporal anchors assume a solar schedule. Restaurants wouldn't know when to serve breakfast versus dinner. Television schedules would become arbitrary. The shared cultural rhythm that binds society would disintegrate. Work productivity would plummet. Humans are diurnal creatures, evolved for daytime activity. Even with artificial light, the absence of natural light reduces alertness, creativity, and motivation. Seasonal companies, ice cream trucks, beach resorts, ski lodges, would lose their reference points. Agriculture, fundamentally tied to seasons and daylight, would cease entirely except in artificial environments. Architecture would suddenly seem absurd. Buildings designed to capture natural light would become monuments to a lost era. South-facing windows, skylights, sunrooms, architectural features prized for millennia, would become pointless. The glass towers that dominate city skylines, designed to maximize daylight, would require constant internal illumination. Light would become currency. Communities with reliable artificial light would thrive while others descended into chaos. LED bulbs would be hoarded. Batteries would be worth more than gold. The inequality between those with access to electrical infrastructure and those without would become a survival divide. Light pollution, once an environmental concern, would become a beacon of hope, proof that civilization persisted in small pockets against the darkness. Photosynthesis stops the instant sunlight disappears. No gradual decline, no adaptive period, just immediate total cessation of the process that produces most of Earth's oxygen and forms the base of nearly every food chain. The last molecules of glucose were created 8 minutes and 20 seconds after the sun went dark, as the final photons completed their journey to Earth. Inside every chloroplast, the elaborate machinery of photosynthesis would fall silent. The photosystems that capture light, the electron transport chains that convert energy, the Calvin cycle that fixes carbon dioxide into sugar, all would stop mid-reaction. Leaves would contain partially processed molecules, frozen in their chemical pathways like a factory abandoned mid-shift. Plants wouldn't die immediately. They store energy as starch, keeping reserves for cloudy days and nighttime respiration. A healthy tree might have enough stored energy to survive weeks in darkness, slowly consuming its starch reserves. But it would be a one-way process. Every moment of respiration would deplete reserves that could never be replenished. Agricultural crops would vary in survival time. Potatoes and other root vegetables store massive amounts of starch underground. They might remain edible for months if prevented from freezing. Grains in silos would stay nutritious until consumed, or until cold destroyed their cellular structure. But growing crops would be impossible. The last harvest would be humanity's final natural food supply. Phytoplankton, the ocean's microscopic plants, produce 70% of Earth's oxygen. These organisms have minimal energy storage, surviving hour to hour on sunlight. Within days, most would exhaust their reserves and die. Their death would cascade through marine food webs. Zooplankton that eat phytoplankton would starve. Then fish that eat zooplankton. Then larger predators. The ocean would become a vast graveyard. Interestingly, Earth's oxygen wouldn't disappear immediately. The atmosphere contains about 1.2 million billion tons of oxygen, built up over billions of years. Without photosynthesis replacing what we breathe, and assuming all current oxygen consumption continued, we'd have roughly 3,000 years of breathable air. But this assumes no increase in consumption from decaying plant matter, or desperate attempts to generate heat through combustion. Some plants would attempt emergency responses. Many species can sense light quality and duration, triggering dormancy in winter. But this darkness would be absolute, beyond any evolutionary preparation. Seeds would remain viable in the frozen ground, containing genetic instructions for a world that no longer existed. They would be time capsules of photosynthetic life, waiting for a sun that would never return. Greenhouse operations with artificial lighting would become humanity's only source of fresh produce. LED grow lights can provide the specific wavelengths plants need for photosynthesis. But the energy requirements would be enormous. Growing enough food for even a small population would require nuclear reactors or geothermal power plants dedicated solely to agricultural lighting. The nitrogen cycle would collapse without plants. Nitrogen-fixing bacteria in root nodules would die with their plant hosts. The careful balance of nitrogen compounds in soil, essential for plant growth, would become irrelevant. Fertilizers stockpiled for spring planting would never be used. The entire agricultural infrastructure, tractors, irrigation systems, pesticides, would become useless artifacts. Forests would transform into standing graveyards. Trees would remain upright, frozen in place, but dead. Without decomposer organisms, which also need warmth, they wouldn't rot normally. Earth would be covered in flash-frozen plant architecture, preserved like specimens in a cosmic museum. Future archaeologists, if any existed, would find perfectly preserved leaves, with chloroplasts still visible under microscopes. Herbivores would face immediate crisis. Cattle, sheep, horses, all would quickly exhaust available plant matter. Carnivores might survive longer, feeding on dying herbivores, but the collapse would be swift and complete. The food pyramid would crumble from the bottom, each level failing as its foundation disappeared. Within months, only scavengers and decomposers would remain, and even they would eventually run out of material to process. The animal kingdom would react to eternal darkness, with behaviors ranging from confused to catastrophic. Every species has evolved specific responses to light cycles, and the sudden break in this fundamental pattern would trigger a cascade of maladaptive behaviors that would doom most complex life. Birds would be among the first casualties. Most species navigate using a combination of magnetic fields, star positions, and solar angles. Without the sun, two of these three navigation tools would vanish. Migrating birds in flight would become disoriented immediately, circling in confusion until exhaustion forced them to land. Those on the ground would attempt to roost, thinking night had fallen, but would never receive the dawn signal to resume activity. Nocturnal animals would initially thrive in the eternal darkness. Owls, bats, and nocturnal rodents would emerge, finding their normally limited hunting time extended indefinitely. But this advantage would be temporary. Nocturnal predators depend on diurnal prey being active during daylight. With all animals shifted to darkness behavior, normal predator-prey cycles would collapse. Owls would find no mice foraging in fields. The mice would be hidden in burrows, waiting for a dawn that would never come. Marine animals would face unique challenges. Many fish species migrate vertically in the water column daily, rising to feed at night and descending during day. Without light cues, this vertical migration would cease. The ocean's biological pump, which moves nutrients through different depths, would fail. Fish that hunt by sight would be unable to find prey. Only species adapted to the permanent darkness of deep ocean would maintain normal behavior. Insects, which comprise most of Earth's biodiversity, would experience massive die-offs. Many insects navigate by maintaining a constant angle to the sun or moon. Moths spiraling into flames demonstrate this navigation system, malfunctioning around artificial lights. In total darkness, flying insects would lose all orientation. Pollinators like bees, which use the sun's position to communicate flower locations through dance, would be unable to forage effectively. Mammals would show varied responses based on their sensory adaptations. Species that rely primarily on smell and hearing, like dogs, would adapt better than visually oriented species like humans and most primates. But all mammals would face the same fundamental problem. Their food sources would be disappearing. Herbivores would find no plants. Carnivores would eventually find no herbivores. The confusion would manifest in heartbreaking ways. Dairy cows would wait at barn doors for sunrise milking that would never come. Roosters would crow randomly, having lost their solar trigger. Dogs would whine at doors, expecting morning walks in permanent midnight. Cats, naturally crepuscular, active at dawn and dusk, would search endlessly for these transition periods. Zoo animals would present immediate crisis. Tropical species housed in temperate zones would die quickly as heating systems failed. Elaborate life support systems that maintain specific light cycles for different species would become impossible to sustain. Zookeepers would face impossible choices about which animals to try to save with limited resources. Hibernation cycles would malfunction catastrophically. Bears, groundhogs, and other hibernators use day length to trigger torpor. The eternal darkness might send them into hibernation, but without spring's lengthening days to trigger awakening, they would never emerge. They would die in their dens, their metabolisms slowed, but still consuming energy reserves that evolution never designed to last forever. Communication systems would break down. Birds sing at specific times related to sunrise. Wolves howl at particular portions of night. Fireflies flash in patterns timed to darkness phases. All these communication methods assume light-dark cycles. Animals would be calling out of sync, their messages lost in temporal chaos. Perhaps most tragically, parental care would fail. Many species time reproduction to seasons, ensuring offspring arrive when food is plentiful. Parents feed young on schedules tied to daylight. Without these cues, breeding would cease or become chaotic. Eggs would be laid at wrong times, nests built in inappropriate conditions. Young abandoned as parents struggled with their own survival. 1 week after the sun's death, Earth's average surface temperature would plummet to 0 degrees Fahrenheit, minus 18 degrees Celsius, transforming our planet into a frozen sphere hostile to most life. The cooling process would create distinct zones of survivability, with dramatic temperature gradients developing between surface and subsurface environments. The freezing would begin at the surface and work downward, following the laws of thermodynamics. Ground frost would penetrate soil at roughly 1 inch per day in temperate regions, faster in areas with less moisture. This frost line would be death's frontier, killing root systems and soil organisms as it descended. Within a week, the frost would reach 6 to 8 inches deep, beyond the reach of most plant roots and burrowing insects. Lakes would develop ice covers following predictable patterns. Ice forms first at shores and surfaces, growing thicker at roughly 2 inches per day in calm conditions. A week into darkness, small ponds would be frozen solid. Larger lakes would have ice thick enough to walk on, though liquid water would persist below. The Great Lakes would take months to freeze completely, their massive volume resisting the cold. Ocean freezing would begin at the poles and spread toward the equator. Sea ice formation releases salt, creating dense brine that sinks, potentially maintaining circulation temporarily. The Arctic Ocean, already partially frozen, would seal completely within days. The Antarctic Ocean would follow. By week's end, ice would be forming as far south as Scotland in the Atlantic, as far south as Oregon on the Pacific American coast. The atmosphere itself would begin to condense. Carbon dioxide freezes at negative 78 degrees Fahrenheit, negative 61 degrees Celsius at sea level pressure. While surface temperatures wouldn't reach this immediately, the upper atmosphere would. Dry ice snow would begin falling at high altitudes, creating a bizarre weather phenomenon never seen on Earth. This CO2 snow would sublimate, turn directly from solid to gas when it reached warmer lower altitudes, at least initially. Rivers would freeze from edges inward, creating ice dams that would cause flooding before everything solidified. Moving water resists freezing, so rapids and waterfalls would continue flowing longer than still water. Niagara Falls might continue for weeks, creating spectacular ice formations in the darkness before eventually freezing solid. Underground springs would be the last flowing water, protected by Earth's insulation. Cities would become ice sculptures. Water pipes would burst as ice expanded, creating frozen waterfalls from buildings. Streets would be glazed with ice from the last rain and snow. Cars would be entombed in ice shells. Skyscrapers would creak and groan as materials contracted at different rates. Windows would shatter from thermal stress, littering streets with glass that would remain sharp forever in the preserving cold. The temperature gradient between surface and depth would create unique phenomena. Subway tunnels, insulated by earth and concrete, might remain above freezing while streets above -20 degrees Fahrenheit. This would drive massive air movements as cold, dense air tried to sink into warmer spaces. Tunnel entrances would become wind tunnels, with frigid air pouring down stairs and escalators like invisible waterfalls. Snow would be strange in this new world. Without sunlight to create temperature variations, there would be no weather fronts, no storm systems. The last snow would be whatever moisture remained in the atmosphere when temperatures dropped below freezing. After that, precipitation would cease. The ground would be covered with this final snowfall, preserved perfectly without melt-freeze cycles, like the surface of Neptune's moon Triton. Geothermal regions would create pockets of warmth in the frozen wasteland. Iceland's volcanic activity would maintain liquid water in some areas. Yellowstone's hot springs would continue steaming, though the steam would instantly freeze into ice crystals, creating constantly growing ice formations. These regions would become beacons for any surviving life, islands of warmth in an increasingly frozen ocean. The psychological impact of the cold would compound the darkness trauma. Cold is painful, demanding constant attention. The need for heat would override all other concerns. Humanity would huddle around whatever heat sources remained, watching their breath freeze in air, knowing that every hour took them further from the warm world they once knew. As the cold deepened and darkness persisted, humanity would face the greatest migration in history. Not across continents, but indoors. Every heated building would become a lifeboat. Every warm room a contested refuge. The social fabric of civilization would stretch and tear as billions sought shelter in spaces designed for millions. The migration would begin gradually. People would first return to their homes, assuming this was temporary. But as temperatures plummeted and power systems strained, those in poorly insulated houses would seek better shelter. Apartment buildings with central heating would fill with refugees from suburban homes. Hotels would be overwhelmed. Every space with functioning heat would accumulate desperate occupants. Public buildings would be commandeered for survival. Shopping malls, with their large enclosed spaces and backup generators, would transform into refugee camps. Thousands would cluster in department stores, sleeping between clothing racks, using furniture displays as living spaces. Food courts would become communal kitchens until supplies ran out. The familiar commercial spaces would morph into primitive tribal territories. Schools and hospitals would face impossible decisions. Schools might close, sending children home, only to reopen as emergency shelters when homes became unlivable. Hospitals, needing to maintain life support systems, would have to turn away non-critical refugees to preserve power. Medical ethics would collapse under survival arithmetic. How many refugees could they accept before compromising patient care? Underground spaces would become premium real estate. Subway stations, naturally insulated and often heated by train operations and human density, would fill with refugees. Every platform would be carpeted with humans. Maintenance tunnels would house families. The sophisticated transit systems of major cities would devolve into underground refugee cities, governed by whoever controlled access points. Social hierarchies would reshape around heat access. Building superintendents would wield enormous power, deciding who could enter boiler rooms. Those with fireplace homes would become nobility if they had wood supplies. Possession of a generator would make someone wealthy beyond measure. The comfortable middle-class existence would vanish, replaced by a brutal calculus of proximity to heat. Government buildings would attempt to maintain order while being overwhelmed themselves. City halls would declare themselves emergency coordination centers, while their lobbies filled with freezing citizens. Police stations would try to maintain law enforcement, while their own facilities became shelters. The contradiction between maintaining authority and providing refuge would tear institutions apart. Churches, temples, and mosques would open doors to all faiths, becoming true sanctuaries. Religious differences would temporarily dissolve in the face of shared survival needs. Pews would become beds. Altars would be surrounded by sleeping families. The spiritual comfort these spaces provided would be matched by their practical value as large, often well-built structures. Apartment buildings would undergo rapid social reorganization. Upper floors, harder to heat, would be abandoned. Everyone would crowd into lower levels. Hallways would be sealed to conserve heat. Individual apartments would merge into communal spaces. Privacy would become an unaffordable luxury. Strangers would share beds for warmth, setting aside social conventions for survival. The wealthy would initially retreat to prepared shelters. Luxury bunkers built for different apocalypses would serve well for this one. But their isolation would become a vulnerability. Without community support, when systems failed or supplies ran out, they would be forced to emerge and negotiate with the masses they had abandoned. Money would be worthless. Heat and food would be the only currencies. Violence would erupt at shelter boundaries. Doorways would become battle lines. Those inside would barricade entrances. Those outside would try to force entry. The moral weight of turning away freezing humans would break many people. Others would harden, accepting that not everyone could be saved. Armed guards at warm buildings would become common, then normal, then necessary. The concept of property would evolve rapidly. Ownership would mean nothing if you couldn't defend it or heat it. Squatters' rights would be determined by who could maintain warmth. Beautiful homes would be stripped for firewood. Priceless artwork would be burned for minutes of heat. The material accumulation of civilization would be consumed in the desperate effort to stay warm. Weather, as humanity understands it, would cease to exist within the first week of darkness. The complex atmospheric dynamics driven by solar heating would collapse, leaving Earth with a still, cold atmosphere utterly unlike anything in our planet's history. The engine that drives weather, temperature differences between regions, would sputter and die as the entire globe cooled uniformly. Wind is born from pressure differences caused by unequal heating. The equator receives more solar energy than poles, creating circulation patterns. Hot air rises, cold air sinks, and the planet's rotation creates the Coriolis effect that spins hurricanes and shapes jet streams. Without the sun, these temperature gradients would vanish. The last winds would blow as remaining heat dissipated. Then Earth would fall still. The jet streams, those rivers of fast-moving air that circle the globe at 30,000 feet, would slow and disappear within days. Commercial aviation, if it still existed, would lose the tailwinds that speed eastbound flights. Weather forecasters would watch their models fail as the fundamental assumptions, solar input, convection, pressure systems, became obsolete. The last weather forecast would be simple: cold and getting colder, forever. Storms require energy, and that energy comes from the sun. Hurricanes feed on warm ocean water. Thunderstorms develop when surface heating creates instability. Tornadoes form when different air masses collide. None of these phenomena could exist without solar heating. The violence of Earth's weather would be replaced by an eerie calm more complete than any human has experienced. The water cycle would grind to a halt. Evaporation requires heat energy to transform liquid water to vapor. Without the sun, no new water vapor would enter the atmosphere. The last clouds would be those already formed, and they would precipitate out as snow or ice crystals within the first few days. After that, Earth's skies would be forever clear, if you could call the starlit darkness sky. Ocean currents, driven by wind and temperature differences, would cease. The Gulf Stream, which keeps Europe warm, would stop flowing. The global conveyor belt of ocean circulation that distributes nutrients and regulates climate would freeze in place. The ocean would stratify into layers that would never mix again, with the densest water settling to the bottom, creating a static, lifeless sea. Atmospheric pressure would change dramatically as gases began condensing. Water vapor would freeze out first, then carbon dioxide at higher altitudes. The atmosphere would literally shrink, falling as snow and frost. Air pressure at sea level would drop steadily. The composition would shift too, without photosynthesis adding oxygen or removing CO2, and with different gases condensing at different temperatures, we'd breathe an increasingly alien atmosphere. The silence would be profound. Weather creates sound, wind through trees, rain on roofs, thunder across valleys. Without weather, Earth would fall into a silence deeper than the quietest desert night. No leaves would rustle, no waves would crash on shores once they froze. The only sounds would be human-made, or the crack of ice forming and the groans of materials contracting in the cold. Humidity would plummet to zero as all moisture froze out of the air. The dry atmosphere would desiccate everything exposed to it. Wooden structures would crack, paper would become brittle. Human skin would require constant moisturizing to prevent painful cracking. Static electricity would build to dangerous levels with no humidity to dissipate charges. Every surface would become a shock hazard. The psychological impact of weather's absence would be profound. Humans have evolved with weather as a constant companion, a source of variety, beauty, and danger. The loss of weather would remove a fundamental aspect of earthly experience. No more rain to sleep to, no more snow days, no more spring storms or autumn winds. Just eternal, still, cold darkness. This stillness would be weather's final gift, making the cold slightly more bearable by eliminating wind chill, but also removing any hope that conditions might change. The electrical infrastructure humanity depends on would face immediate, overwhelming strain the moment darkness fell. Power grids designed for predictable day-night cycles would confront unprecedented demand as every light, heater, and electrical system activated simultaneously. The cascade of failures would begin within hours and accelerate over days. Baseload power plants, nuclear, coal, and natural gas facilities that provide steady electricity would initially continue operating, but they were designed assuming only 60 to 70% peak usage. With eternal darkness, demand would spike to 150 to 200% of normal peaks. Grid operators would watch helplessly as transmission lines overheated, transformers overloaded, and circuit breakers tripped to prevent total system meltdown. Rolling blackouts would begin within the first day, carefully managed attempts to preserve the grid by cutting power to different regions in rotation. But these measures assume temporary crisis. As temperatures dropped and darkness persisted, the blackouts would become permanent for increasingly large areas. Priority would go to hospitals, government facilities, and emergency services. Residential areas would be abandoned by the grid. Coal plants would face unique challenges. Many rely on trains delivering fuel daily. In the chaos and darkness, rail transport would become dangerous and unreliable. Coal stockpiles at plants typically last 30 to 60 days. Once depleted, these massive facilities would fall silent. The conveyor belts, crushers, and furnaces that turned fossil fuel into electricity would freeze solid, becoming industrial monuments to a lost age. Natural gas plants would fare better initially. Gas flows through pipelines that could operate temporarily without power, using line pressure. But compressor stations that maintain pipeline pressure require electricity. As the grid failed, gas pressure would drop, starving turbines of fuel. The vast network of pipelines crossing continents would depressurize and fail within weeks. Nuclear plants would become islands of power and heat in the darkness. Their fuel lasts 18 to 24 months between refueling. They could theoretically operate until fuel exhausted. But nuclear plants require massive amounts of cooling water. As rivers and cooling ponds froze, reactors would be forced to shut down or risk meltdown. The controlled shutdown of nuclear facilities would require careful management to avoid disasters. Renewable energy would fail immediately. Solar panels would be useless decorations. Wind turbines might continue briefly, but without temperature differences to drive wind, they would soon stand motionless. Hydroelectric dams would operate until reservoirs froze, then turbines would seize as ice destroyed the delicate machinery. The green energy revolution would be revealed as completely dependent on the sun. Battery backup systems would be depleted within hours or days. Uninterruptible power supplies in data centers would maintain critical systems briefly, then fail. Electric vehicles would become one-time use batteries, their power drained for heat and light until dead forever. The chemical reactions in batteries slow dramatically in extreme cold, reducing capacity just when needed most. The failure wouldn't be uniform. Remote communities with local generation might maintain power longer than cities dependent on distant plants. Military bases with hardened infrastructure would preserve capabilities while civilian grids collapsed. But these would be temporary reprieves. Without fuel deliveries, maintenance, and warm workers, every system would eventually fail. Emergency generators would run until fuel exhausted. Hospitals would face horrible decisions: which life support systems to maintain, which to shut down. Diesel fuel would gel in the cold, requiring constant heating to remain liquid. Generator engines would struggle in the frigid air, consuming more fuel for less output. The backup systems designed for temporary outages would be pushed beyond all design limits. Amateur radio operators would become critical communication links as mainstream systems failed. Ham radios, powered by car batteries or small generators, would maintain contact between isolated communities. The airwaves would fill with desperate calls for help, information, and human contact. These volunteers would be civilization's nervous system as its body died. The grid's death would be visible from space, if anyone remained to watch. The bright networks of light-marking cities would dim and disappear, region by region. The eastern seaboard's megalopolis would fragment into isolated points. Las Vegas's neon would go dark forever. The last lights would be those nearest to remaining power sources: nuclear plants operating until fuel exhausted, geothermal facilities in Iceland, underground military installations. Then they too would fail, and Earth would be dark not just from above, but from within. The oceans, covering 71% of Earth's surface and containing 97% of its water, would become humanity's last buffer against the cosmic cold. With an average depth of 12,100 feet and enormous heat capacity, the seas would cool slowly, buying precious time for any survival efforts. But this thermal reserve would be finite, and its depletion would mark critical transitions in Earth's death. Water's unique properties would govern the cooling process. Unlike most substances, water reaches maximum density at 39 degrees Fahrenheit, 4 degrees Celsius, not at freezing. This means cold water sinks until reaching this temperature, then further cooling makes it rise. This quirk would preserve liquid water beneath ice far longer than if water behaved normally. Lakes and oceans would freeze from top down, insulating remaining liquid beneath. The ocean's surface would begin forming ice within days at the poles, weeks at temperate latitudes, and months near the equator. But the deep ocean, with average temperatures around 39 degrees Fahrenheit, would remain liquid far longer. The abyssal depths contain water that hasn't seen the surface for centuries. This ancient, cold but liquid water would persist even as the surface world froze solid. Coastal areas would experience moderated temperatures as oceans release their stored heat. Harbour cities like San Francisco, London, and Tokyo would remain several degrees warmer than inland areas. This thermal difference would create temporary local winds, the last weather Earth would experience. People would migrate to coasts, crowding into zones where the ocean's warmth made survival slightly easier. The formation of sea ice would fundamentally alter ocean chemistry. As seawater freezes, it expels salt, creating dense brine that sinks. This process would initially maintain some circulation as supersaline water descended and slightly warmer water rose. But without wind and solar heating to drive circulation, this convection would slow and eventually stop, leaving the ocean stratified in still layers. Marine ecosystems would collapse in stages. Surface plankton would die first, followed by fish that depend on them. Deep-sea creatures near thermal vents would survive longest, sustained by Earth's internal heat rather than solar energy. These oases of chemosynthetic life would persist for potentially thousands of years, the last ecosystems on Earth thriving in pitch darkness as they always have. The ice covering would thicken at roughly 1 meter per month in calm conditions. Wave action would cease as the surface froze, eliminating the mixing that oxygenates water. The ocean would become anoxic, except near the few remaining sources of thermal circulation. Fish would suffocate en masse, their bodies sinking into the depths where cold would preserve them indefinitely. Icebergs would cease forming. These require glaciers flowing into the sea, but without precipitation to build glaciers, no new ice would feed the system. Existing icebergs would freeze into the expanding sea ice, becoming permanent features of the frozen seascape. The dramatic carving events that marked climate change would be replaced by static, eternal ice. Submarines, if any remained operational, would find an alien ocean. Navigation by sonar would work, but the acoustic properties would be different in the still stratified water. They could surface through thin ice initially, but as the covering thickened, they would be trapped beneath, unable to break through. Nuclear submarines could theoretically operate until reactor fuel was exhausted, becoming humanity's last mobile vessels. The salt concentration in remaining liquid water would increase as pure water froze out. The Dead Sea effect would occur globally, increasing salinity, lowering the freezing point, keeping some water liquid at temperatures that should freeze pure water. The last liquid ocean would be a hypersaline layer beneath kilometers of ice, possibly hosting extremophile bacteria adapted to such conditions. Tidal forces from the moon would continue, but their effects would change. Instead of raising and lowering liquid water, tides would stress and crack the ice shell. These tidal flexures would create fractures and pressure ridges, similar to those on Jupiter's moon Europa. The similarities would be more than superficial. Earth would essentially become a Europa-like ice world, with a frozen shell over a liquid ocean. The ocean's thermal death would take years to complete. Models suggest the surface would be entirely frozen within 1 year, with ice thickness reaching 10 to 50 meters. Complete freezing to the seafloor would take much longer, perhaps millennia for the deepest trenches. The death of Earth's biosphere would unfold with mathematical precision, each trophic level collapsing as its foundation disappeared. Within a month of the sun's extinction, Earth would witness the most rapid mass extinction in its 4 billion-year history, surpassing even the Permian-Triassic event that killed 96% of marine species. The extinction would follow thermodynamic laws. Smaller organisms with higher metabolic rates would die first. Insects, with their limited fat reserves, would perish within days. A housefly needs to eat every few hours. Without food or warmth, they would drop dead within a day. Beneficial insects, pollinators, decomposers, soil aerators, would vanish, taking their ecological services with them. The intricate web of relationships built over millions of years would unravel in weeks. Mammals would face varied fates based on size and adaptation. Small rodents, with their high surface area to volume ratios, would lose heat rapidly and die within days unless they found warm shelter. Larger mammals would last longer, their body mass providing temporary insulation. An elephant might survive a week, a mouse merely hours. Hibernating species would enter torpor but never wake, dying peacefully in their sleep. Birds would suffer particularly brutal deaths. Their high metabolic rates demand constant food intake. A chickadee must eat its body weight daily in winter. Without insects or seeds, they would starve within 24 to 48 hours. Migrations would become death marches. Arctic terns, which fly from pole to pole, would drop from the sky mid-journey. The dawn chorus that has greeted every sunrise for millions of years would fall silent forever. Reptiles and amphibians, being ectothermic, would simply stop moving as temperatures dropped. Unable to generate body heat, they would slip into torpor, then death. Tropical species would die almost instantly. Desert reptiles, adapted to temperature extremes, might last days, but all would eventually freeze solid, preserved perfectly in whatever position they last occupied. Ocean extinctions would cascade through food webs. Coral reefs, already stressed by climate change, would bleach and die within days. The symbiotic algae that feed them through photosynthesis would cease functioning immediately. These rainforests of the sea, supporting 25% of marine species, would become calcium carbonate graveyards. Fish dependent on coral would die within weeks, followed by their predators. The microbial world would experience selective devastation. Photosynthetic bacteria would cease functioning immediately. But chemosynthetic bacteria around volcanic vents would continue. Extremophiles in deep rock formations, some living miles below the surface, wouldn't notice the sun's absence for potentially millions of years. These would be Earth's last life forms, persisting long after complex life vanished. Domestic animals would face horrible fates. Pets would die alongside their owners or be abandoned to freeze. Livestock in barns might survive days if structures retained heat, but without food, they would starve. Factory farms would become mass graves. Free-range animals would last slightly longer, but face the same inevitable end. The 10 billion chickens, billion cattle, and billion pigs that feed humanity would die within weeks. Fungi would briefly thrive on the massive die-off, decomposing bodies in a final recycling of nutrients. But even they require temperatures above freezing for active growth. They would slow, then stop, leaving bodies partially decomposed. Earth would be littered with freeze-dried corpses that would never fully decay, preserved like specimens in a cosmic museum. Seeds and spores would remain viable but dormant. Buried in soil or stored in facilities, they would contain the genetic blueprints for life that could never germinate. The Svalbard Global Seed Vault, designed to preserve crop diversity, would maintain its -18°C temperature naturally. Its precious cargo would be perfectly preserved but utterly useless, time capsules for a future that would never come. Extinction debt, species doomed but not yet dead, would be universal. Every organism would be functionally extinct the moment the sun died, even if individuals survived days, weeks, or months. No reproduction would be possible. No new generations would emerge. Evolution would cease. The great experiment of life on Earth, 3.8 billion years of increasing complexity and diversity, would end not with a bang, but with a freezing whimper. By the 1-month mark, 99.9% of species would be extinct. Only the most extreme organisms in the most sheltered environments would persist. Earth would transition from a living world to a fossil record, preserved in ice. Earth's atmosphere contains approximately 1.2 million billion tons of oxygen, accumulated over billions of years of photosynthesis. With photosynthesis ceased, this reservoir would begin depleting immediately, but the timeline for atmospheric oxygen loss would be surprisingly long, and surprisingly irrelevant for human survival. The mathematics of oxygen depletion are straightforward but sobering. Humanity collectively breathes about 7 billion tons of oxygen annually. All animal life combined consumes perhaps 100 billion tons yearly. If consumption continued at current rates with no replacement, atmospheric oxygen would last roughly 12,000 years. But this assumes stable consumption, which wouldn't happen as life rapidly died off. The immediate oxygen consumers would be fires. In the first days of darkness, humanity would burn anything combustible for heat and light. Every fireplace, every barrel fire, every burning building would consume oxygen while producing carbon dioxide. A single house fire can consume the oxygen equivalent of what 1,000 people breathe daily. Widespread burning would accelerate oxygen depletion far beyond biological respiration. Decomposition would be another major oxygen sink, initially. The massive die-off of plant and animal life would create billions of tons of organic matter requiring decomposition. Aerobic bacteria breaking down this material would consume vast amounts of oxygen. But as temperatures plummeted, decomposition would slow, then stop. Bodies would freeze before they could rot, paradoxically preserving oxygen. The changing atmospheric composition would create subtle but important effects. Current atmosphere is 78% nitrogen, 21% oxygen, 0.04% carbon dioxide. As oxygen decreased and CO2 increased, the air would become increasingly toxic. At 17% oxygen, humans experience impaired judgment. At 15%, physical coordination fails. At 10%, consciousness is lost. But we'd never reach these levels. Cold would kill us millennia before oxygen depletion. Carbon dioxide accumulation would be the more immediate threat. Without photosynthesis removing it, CO2 levels would rise from the current 420 parts per million. At 1,000 parts per million, people experience drowsiness. At 5,000 parts per million, breathing becomes labored. At 40,000 parts per million, unconsciousness occurs within minutes. In sealed shelters where humans gathered, CO2 poisoning would kill before cold or oxygen loss. Ocean absorption would temporarily buffer atmospheric changes. Cold water absorbs gases more readily than warm water. As oceans cooled, they would absorb both oxygen and carbon dioxide, slightly slowing atmospheric changes. But once the oceans froze, this buffer would disappear. The ice would seal the ocean from the atmosphere, preventing gas exchange. The stratification of gases would become pronounced in the still air. Without wind to mix the atmosphere, heavier carbon dioxide would settle in valleys and low areas, creating invisible pools of deadly gas. Oxygen, slightly lighter, would be more prevalent at higher elevations. Mountain settlements would have marginally better air quality than valleys, though the difference would be academic, given the lethal cold. Artificial oxygen production would be possible, but energy-intensive. Electrolysis can split water into hydrogen and oxygen, but requires enormous electrical power. Nuclear submarines and space stations use this technology, but scaling it for large populations would be impossible without massive power generation. A small colony might maintain breathable atmosphere, but not a civilization. The freezing out of atmospheric components would alter the oxygen percentage. Water vapor would freeze first, then carbon dioxide at higher altitudes and polar regions. As these gases left the atmosphere as snow and frost, the relative percentage of oxygen would actually increase slightly. The atmosphere would shrink, but become marginally more oxygen-rich, though at lower overall pressure. The psychological impact of monitoring oxygen levels would be severe. Unlike temperature, which is immediately felt, oxygen depletion is insidious. People would install CO2 detectors in shelters, watching the numbers climb inexorably. The knowledge that Earth's breathable atmosphere was slowly degrading would add another layer of doom to an already hopeless situation. Remarkably, if humanity somehow survived the cold, darkness, and starvation, oxygen wouldn't be the limiting factor. The atmosphere contains enough oxygen for thousands of years of breathing. We would freeze to death millennia before suffocating. The oxygen clock would outlast humanity by eons, continuing to tick in an empty, frozen world where nothing remained to breathe it. The persistence of oxygen would be Earth's final irony, maintaining an atmosphere perfect for life that no longer existed. In the frozen darkness, human survival would concentrate around Earth's remaining energy sources: geothermal hotspots, nuclear facilities, and deep underground bunkers with independent power. These locations would become the final bastions of technological civilization, islands of warmth and light in a dead world. Iceland would emerge as humanity's most viable refuge. The island sits atop the mid-Atlantic ridge, where tectonic plates spread apart, allowing magma to approach the surface. Geothermal energy provides 85% of Iceland's heating and 25% of its electricity today. This infrastructure would continue functioning without the sun. Reykjavik's sophisticated geothermal heating system could maintain livable temperatures indefinitely, powered by Earth's internal heat. The technical requirements for geothermal survival are substantial, but achievable. Deep wells tap water heated by magma, bringing steam to the surface to drive turbines. This process requires no external fuel, no supply chains, no solar input. As long as Earth's core remains hot, billions of years, geothermal energy would flow. Iceland's 350,000 residents could theoretically survive indefinitely, though food production would require artificial growing facilities. Yellowstone would become North America's survival hub. The caldera's geothermal features could support settlements around hot springs and geysers. Old Faithful would continue erupting on schedule in the darkness, each eruption a reminder that Earth still lived beneath its frozen surface. The challenge would be harnessing this energy quickly enough. Unlike Iceland's developed infrastructure, Yellowstone would require rapid construction in lethal conditions. Nuclear power plants would offer temporary refuge. The 440 operational reactors worldwide would become fortified settlements. Each plant generates enormous heat, most of which is normally waste dumped into cooling water. This waste heat could warm thousands of people. Nuclear plants also have backup generators, water treatment facilities, and security infrastructure. They're designed to operate in isolation during emergencies. The lifespan of nuclear refugees would depend on fuel supplies. Most plants refuel every 18 to 24 months. Without the industrial infrastructure to produce new fuel rods, reactors would eventually exhaust their fissile material. The last operational reactors would be those most recently refueled when darkness fell. After fuel exhaustion, these sites would become frozen tombs, filled with sophisticated but useless technology. Military bunkers designed for nuclear war would prove their worth in this different apocalypse. Cheyenne Mountain, the Swiss government's bunker network, Russia's Yamantau mountain complex. These facilities were built to sustain populations for years without surface contact. They have air filtration, water recycling, food storage, and independent power generation. Their psychological preparation for isolation would prove as valuable as their physical infrastructure. Deep mines would offer unexpected sanctuary. The deepest gold mines in South Africa descend over 2 miles, where rock temperatures reach 140 degrees Fahrenheit. Mines require cooling for normal operation, but in a frozen world, this heat would be life-saving. Mining communities could retreat underground, using existing tunnels and equipment. The Wieliczka salt mine in Poland, with its underground cathedral and lakes, could house thousands. Submarine bases would leverage nuclear submarine technology for survival. A Virginia-class submarine's reactor produces 40,000 horsepower and can operate for 33 years without refueling. Submarines already recycle air and water, grow food in small hydroponic gardens, and operate in complete darkness. Naval bases could become survival colonies, with submarines serving as power plants and life support systems. The social organization of survival hubs would be crucial. Resources would be finite. Geothermal sites have maximum capacity. Nuclear plants have specific operational requirements. Strict population controls would be necessary. Who decides who lives in the warm zones? What skills qualify someone for survival? These decisions would tear apart conventional morality, replacing it with brutal pragmatism. Food production in survival hubs would require revolutionary approaches. LED-lit hydroponic farms could grow vegetables using geothermal or nuclear power. Protein might come from insect farming. Crickets efficiently convert feed to protein and thrive in warm, dark conditions. Mushroom cultivation could recycle organic waste. But feeding even small populations would require massive infrastructure. The greatest challenge would be maintaining technology. Complex systems require constant maintenance, spare parts, and skilled operators. Without global supply chains, each hub would need to manufacture everything locally. 3D printing might allow some production, but raw materials would be limited. Eventually, high technology would fail, replaced by whatever could be built and maintained locally. These hubs wouldn't be saving humanity. They'd be providing hospice care for the species, extending survival by years or decades, rather than achieving permanence. 1 year after the sun's death, Earth would complete its transformation into an ice world resembling Jupiter's moon Europa, more than the blue marble we once knew. The surface would be entirely frozen, with ice sheets extending from pole to pole, entombing the planet in a crystalline shell that would preserve the final moments of a once living world. Ocean ice would average 50 meters thick at the equator, over 200 meters at the poles. This wouldn't be smooth ice, but a tortured landscape of pressure ridges, cracks, and refrozen leads. Tidal forces from the moon would continue stressing this shell, creating fractures that might briefly expose liquid water before freezing again. These fracture patterns would be the only dynamic features on an otherwise static surface. The atmosphere would have dramatically thinned. Water vapor, completely frozen out, would exist only as ice crystals on the surface. Carbon dioxide would have partially frozen at the poles and high altitudes, creating deposits of dry ice. The atmospheric pressure would drop to perhaps 600 millibars, equivalent to being at 14,000 feet elevation today. The air would be thin, dry, and composed primarily of nitrogen and oxygen. Land surfaces would be buried under snow and ice, but not uniformly. Areas that received the last precipitation would have deeper coverage. Windward mountain slopes might have 100-meter ice accumulations, while desert regions might show exposed rock through thin frost layers. Cities would be partially buried, their skylines protruding through ice like geometric mountain ranges. Interesting ice formations would develop where geology met the frozen surface. Volcanic regions would create ice caverns and tunnels as geothermal heat met surface cold. These would be spectacular, massive ice crystals, frozen waterfalls, caves lined with frost feathers. But they would exist in absolute darkness, unseen and unseeable, beauty without observers. The color palette of Earth from space would be monochromatic. The blue oceans, green forests, brown deserts, and white clouds would be replaced by uniform white and grey. The planet would reflect most incoming starlight, appearing as a dim, featureless sphere. Earth's albedo would approach 0.9, reflecting 90% of received radiation, though with no sun, this would be purely academic. Lakes would be frozen to their bottoms, except for the very deepest. Lake Baikal, the world's deepest at 1,642 meters, might retain liquid water in its depths. This water would be ancient, trapped beneath ice, experiencing no circulation or mixing. The unique species that evolved in Baikal over millions of years would be extinct, but their bodies would be preserved in the ice, like insects in amber. Underground water would persist longer. Deep aquifers, insulated by rock and warmed by geothermal gradients, would remain liquid. These hidden reserves would be inaccessible to surface dwellers, but might support bacterial life for millennia. The water cycle that connected surface and subsurface would be broken forever, each realm isolated. Glacial dynamics would cease. Glaciers flow because of pressure and temperature gradients that cause basal melting. In the uniform cold, glaciers would freeze solid to bedrock, stopping their million-year journeys. The glacial valleys, moraines, and other features that marked ice age cycles would be preserved in stasis. A geological clock stopped mid-tick. The boundary between land and sea would disappear under ice. Coastlines, those dynamic zones where terrestrial and marine ecosystems meet, would be erased. You could walk from London to New York across the frozen Atlantic. The Pacific would be a traversable ice plain. The distinct geography that separated continents and defined human history would be meaningless. Weather patterns would be completely absent. No storms, no precipitation, no wind beyond minor convection near geothermal sites. The complex atmospheric dynamics that created hurricanes, monsoons, and trade winds would be replaced by stillness. The last weather forecast would be accurate forever, clear, cold, and dark. Seismic activity would continue but with different effects. Earthquakes would still occur as tectonic plates shifted, but their interaction with the frozen surface would be unique. Icequakes would propagate differently than through liquid water. Tsunamis would be impossible. Volcanic eruptions would create temporary hotspots, melting through ice before freezing into bizarre formations. This ice world phase would be Earth's longest epoch, lasting until the planet's internal heat finally dissipated billions of years hence, or until the frozen sun somehow reignited. The cessation of photosynthesis and the freezing of Earth's surface would trigger a cascade of chemical changes, transforming our planet's carefully balanced chemistry into something alien and hostile. The biogeochemical cycles that have regulated Earth's habitability for billions of years would collapse, leaving behind a world whose chemistry would be unrecognizable. The carbon cycle would grind to a complete halt. No photosynthesis would fix atmospheric CO2 into organic matter. No respiration would return it to the atmosphere. The carbon already in living things would be frozen in place. Trees would stand as carbon sculptures, their cellulose and lignin preserved indefinitely. Soil carbon, normally cycled by microbes, would be locked in permafrost. Earth's carbon budget would be frozen in its final configuration. Nitrogen fixation would cease entirely. The bacteria that convert atmospheric nitrogen to biologically available forms require warmth and often plant root associations. Without them, the nitrogen cycle breaks. Existing soil nitrates would be the last available nitrogen for any surviving life. The atmosphere would retain its 78% nitrogen composition, but it would be biologically useless, abundant, yet unavailable. The oxygen-carbon dioxide balance would shift dramatically. Without photosynthesis producing oxygen and consuming CO2, and with minimal respiration occurring in the cold, the atmosphere would slowly trend toward chemical equilibrium. Oxygen would combine with exposed minerals in a process called oxidation, gradually depleting over geological timescales. Iron would rust, even in the cold, though slowly. Ocean chemistry would be revolutionized by freezing. As ice formed, salts would be excluded, creating hypersaline brine channels within the ice and supersaline water below. The ocean's pH would shift as carbonic acid accumulated without photosynthetic consumption. The buffering capacity that has kept ocean chemistry stable would be overwhelmed. The seas would become acidic, though frozen acids pose little threat. Methane hydrates on the ocean floor would remain stable or become even more stable in the cold. These ice-like structures containing trapped methane require specific pressure-temperature conditions. The cooling would push more of the ocean floor into the stability zone for hydrates. Vast amounts of methane would be locked in these frozen cages, a fossil fuel reserve that would never be accessed. The sulfur cycle would be particularly interesting. Volcanic activity would continue releasing sulfur compounds, but without rain to wash them from the atmosphere, they would accumulate. Sulfur dioxide would react with the last atmospheric moisture to form sulfuric acid crystals, frozen acid snow. Volcanic regions would be surrounded by deposits of yellow sulfur and white acid crystals, creating alien landscapes. Soil chemistry would be frozen in transition. The complex interactions between minerals, organic matter, and microorganisms would stop mid-reaction. Nutrients in the process of cycling would be locked in place. The soil would become a chemical museum, preserving the exact state of millions of different reactions at the moment heating ceased. Industrial chemicals would persist indefinitely. Plastics, designed to resist decomposition, would last even longer in the frozen environment. Pesticides, pharmaceuticals, and synthetic compounds would remain wherever they were when the cold arrived. The Anthropocene's chemical signature would be preserved perfectly, a toxic time capsule of human chemistry. Radioactive decay would continue unchanged. Uranium, thorium, and other radioactive elements would keep generating heat and radiation. This would be one of the few remaining energy sources, driving minor local chemistry. Radiolysis, the breaking of chemical bonds by radiation, would slowly alter materials near radioactive deposits. These would be among the only sites where chemistry actively continued. Cave chemistry would create unique environments. Without flowing water, cave formation would cease, but existing caves would become chemical preservation chambers. Stalactites and stalagmites would stop growing, frozen in place. The delicate balance of dissolved minerals would be disrupted. Some caves might maintain liquid water through geothermal heating, creating isolated chemical reactors. The production of new minerals would virtually cease. Mineral formation typically requires water as a medium for chemical reactions. With everything frozen, the geological processes that create new minerals would stop. Earth's mineralogical diversity, over 5,000 known minerals, would be frozen at its current state, with no new minerals forming. Atmospheric escape would gradually alter composition over millions of years. Light gases like hydrogen and helium would slowly escape to space, as they do now, but without replenishment. The atmosphere would gradually become denser in heavy gases, though this process would take eons to produce noticeable changes. Survival in the eternal darkness would depend entirely on technology, complex systems requiring constant maintenance, power, and expertise. The infrastructure needed to sustain even a small human population would be staggering, pushing engineering to its absolute limits, while fighting entropy with increasingly scarce resources. Nuclear fusion reactors, if perfected before the darkness, would be humanity's best hope. Fusion offers effectively unlimited fuel, hydrogen from water, and enormous energy output. A single fusion plant could power heating, lighting, and food production for thousands. But fusion technology requires sophisticated magnetic containment, precise temperature control, and components that would be impossible to manufacture without global supply chains. Life support systems would mirror those on spacecraft, but at larger scales. Air recycling would require mechanical scrubbers to remove CO2, electrolysis to generate oxygen from water, and careful pressure regulation. The International Space Station system supports 7 people using equipment the size of a bedroom. Scaling to thousands would require warehouse-sized facilities, consuming enormous power. Water recycling would be essential and deeply psychological challenging. Every drop would need to be recovered, filtered, and reused. Urine, washing water, and atmospheric moisture would all enter the recycling system. The technology exists. NASA recovers 93% of water on the ISS, but the infrastructure for city-scale recycling would be massive. Psychological acceptance of drinking endlessly recycled water would be another challenge entirely. Food production would require revolutionary approaches. Traditional agriculture would be impossible. LED-lit vertical farms could grow vegetables in stacked trays, achieving high yields in minimal space. But LEDs require electricity, lots of it. Growing enough food for one person for 1 year requires roughly 3,000 kilowatt-hours just for lighting. A 1,000-person colony would need a dedicated power plant just for agriculture. Protein production would likely rely on unconventional sources. Insect farming requires less space, water, and feed than traditional livestock. Crickets convert feed to protein at 12 times the efficiency of cattle. Fungiculture could recycle organic waste into food. Synthetic biology might produce proteins directly from bacteria or yeast, but each system would require precise environmental control, temperature, humidity, atmosphere, all artificially maintained. Manufacturing would be the critical bottleneck. Every tool, component, and replacement part would need to be produced locally once global supply chains collapsed. 3D printing could produce some items, but not everything. Electronic components require rare earth elements and precise fabrication facilities. A single broken component that couldn't be replaced locally could doom an entire survival colony. Medical technology would regress rapidly. Modern medicine depends on global pharmaceutical supply chains. Insulin for diabetics, antibiotics for infections, anesthetics for surgery, all would eventually run out. Colonies would need to manufacture basic medications or return to pre-industrial medicine. Surgery without anesthetics, infections without antibiotics, medical care would become primitive and brutal. Digital systems would face unique challenges. Computer chips perform poorly in extreme cold. Data centers require cooling in normal conditions, but in the deep freeze, they'd need heating to function. The internet would fragment as intercontinental cables failed and satellites died. Each colony would become digitally isolated, preserving whatever knowledge they had stored locally when connections failed. Maintenance would be the slow killer of technological systems, Every machine wears out. Bearings fail, seals degrade, circuits corrode. Without replacement parts, systems would be cannibalized, taking components from less critical systems to keep essential ones running. This would be a one-way process. Once a system was cannibalized, it could never be restored. Technology would slowly contract as colonies chose which systems to preserve. The expertise problem would be equally severe. Operating and maintaining complex technology requires specialized knowledge. Nuclear engineers, hydroponic farmers, water treatment specialists. Each colony would need dozens of specialties, but knowledge would be lost with each death. Training replacements would be difficult without educational infrastructure. Within generations, operational knowledge would degrade. Psychological life support would be as critical as physical systems. Humans need purpose, hope, and social connection. In permanent darkness, facing certain extinction, maintaining mental health would require careful attention. Artificial lighting would need to simulate day cycles. Social spaces would be essential. Entertainment, education, and meaningful work would be necessary to prevent psychological collapse. The energy budget would dominate every decision. Heating living spaces, powering grow lights, running life support. Every joule would be precious. Colonies would face constant triage, heat or food production, medical equipment or water recycling. These zero-sum choices would define existence, with each decision potentially determining who lived and who died. Miles beneath the frozen surface, in the crushing darkness of the deep ocean, life would continue in pockets of warmth around hydrothermal vents. These oases, powered by Earth's internal heat rather than the sun, would be the last functioning ecosystems on the planet, maintaining their alien forms of life long after the surface world died. Hydrothermal vents exist where seawater meets hot volcanic rock, creating chemical-rich environments that support unique ecosystems. The water temperature around vents can exceed 700 degrees Fahrenheit, though it doesn't boil due to extreme pressure. This heat gradient would continue regardless of the sun's status, driven by radioactive decay in Earth's core and mantle. For billions of years to come, these vents would continue pumping heat and chemicals into the deep ocean. The organisms around these vents never relied on sunlight. Chemosynthetic bacteria form the base of the food web, converting hydrogen sulfide and other chemicals into organic matter. Giant tube worms, lacking digestive systems entirely, host these bacteria symbiotically. Ghostly crabs scuttle through the darkness. Eyeless shrimp swarm around the vents. This ecosystem would be Earth's last, unchanged by the catastrophe above. The isolation of the deep ocean would be both its salvation and limitation. The ice ceiling would prevent any exchange with the surface, but also protect the depths from the temperature extremes above. The pressure at depth would prevent freezing even at temperatures below normal freezing point. The deep ocean would become a sealed world, separated from the frozen surface by miles of ice. Water circulation in the deep ocean would slow, but not stop entirely. The heat from vents would create local convection cells, rising plumes of warm water that would cool and sink. This circulation would be much weaker than current thermohaline circulation, but sufficient to distribute some nutrients and maintain minimal mixing. The ocean would stratify into distinct layers that rarely mixed. The biomass around vents is surprisingly substantial. A single vent field can support tons of organisms in an area the size of a football field. The density of life rivals tropical rainforests, though the diversity is lower. These communities grow rapidly. Tube worms can grow 2 meters in 2 years, but are ephemeral. Individual vents last years to decades before shifting geological activity redirects the heat elsewhere. The chemistry of vent ecosystems is toxic to most life. Hydrogen sulfide, the primary energy source, is poisonous to organisms that breathe oxygen. Heavy metals like iron, copper, and zinc precipitate from the vent fluids. The pH can be extremely acidic, yet life thrives in these conditions, using biochemistry completely different from surface organisms. These adaptations would allow vent life to persist unchanged. New vents would continue forming as old ones died. Plate tectonics would continue, driven by Earth's internal heat. Seafloor spreading at mid-ocean ridges would create new crust and new vent sites. The ecosystem would migrate across the ocean floor, following the heat, maintaining continuity across geological time. This process has operated for at least 3.8 billion years and would continue for billions more. The food web around vents is relatively simple but robust. Bacteria form mats and films on rocks. Larger organisms graze on these mats or filter bacteria from the water. Predators like vent crabs and fish eat the grazers. When organisms die, they're quickly consumed by scavengers or decomposed by bacteria. Nothing is wasted in this economy of scarcity. The system is completely self-contained. Some scientists speculate that life on Earth began at hydrothermal vents. The chemical gradients, mineral surfaces, and energy sources provide ideal conditions for the formation of complex organic molecules. In the frozen darkness, these vents would be returning to their possible role as life's cradle, now serving as its final refuge. The genetic diversity around vents is remarkable. Each vent field, isolated from others, evolves unique species. The genetic treasures of these ecosystems, enzymes that function at extreme temperatures, proteins that resist heavy metal poisoning, would be preserved. If Earth somehow warmed again, these organisms could theoretically recolonize the oceans, though the surface world would remain barren without photosynthesis. Exploration of these deep refuges would be impossible for humans. Nuclear submarines couldn't dive deep enough. The pressure, darkness, and cold would be insurmountable. These ecosystems would exist beyond human reach, Earth's last life carrying on without witnesses, demonstrating that life finds a way even in the most extreme circumstances. The question of long-term human survival in eternal darkness ultimately reduces to energy, resources, and population dynamics. With unlimited geothermal or fusion power, proper technology, and careful management, a small human population could theoretically persist for centuries or even millennia. But surviving and thriving would be vastly different concepts in this dark world. The minimum viable population for genetic diversity is debated, but most geneticists suggest 500 to 1,000 individuals to avoid inbreeding depression over generations. This assumes careful genetic management, tracking relationships, controlling reproduction, possibly using artificial insemination to maximize genetic diversity. Every birth would be planned, every death mourned, not just personally, but genetically. Humanity would become a carefully managed breeding program. Energy requirements for this minimum population would be substantial but manageable, assuming 10,000 watts per person for heating, lighting, food production, and life support. A 1,000-person colony would need 10 megawatts continuous power. A single geothermal plant or small nuclear reactor could provide this. Iceland's Hellisheidi power station produces 303 megawatts, enough for 30,000 people under these conditions. Food production would be the limiting factor. Hydroponic vegetables require approximately 50 square meters of growing area per person for a basic vegetarian diet. A 1,000-person colony would need 50,000 square meters, about 12 acres, of climate-controlled growing facilities. With vertical farming, this could be compressed into a smaller footprint, but the infrastructure would be massive. Water wouldn't be scarce, but would require constant recycling. A closed-loop system losing just 1% annually would need replacement sources. In geothermal areas, melting ice would be easy. Nuclear-powered colonies could maintain water treatment indefinitely. But any breakdown in recycling systems would quickly become catastrophic. Water is heavy and bulky. Storing emergency reserves for 1,000 people would be challenging. Psychological sustainability might be the greatest challenge. Humans evolved under open skies with seasonal changes and natural beauty. Permanent underground or enclosed existence would exact a severe psychological toll. Depression, anxiety, and suicide rates would likely be extreme. Children born into this world would know nothing else, but whether they could maintain the psychological resilience needed for survival is unknown. Social organization would need to be radically restructured. Democracy might be impossible when every decision affects survival. Resources would require strict rationing. Individual freedom would be subordinate to collective survival. The society would resemble a military unit or monastery more than any current civilian community. Whether humans could maintain such discipline for generations is questionable. Knowledge preservation would be critical. Each generation would need to master the technology keeping them alive while maintaining knowledge that might not be immediately useful. Mathematics, physics, and engineering would be essential. But would they preserve art, literature, and music? These seem frivolous when survival is precarious, yet they're what makes survival worthwhile. Manufacturing capabilities would gradually degrade. Complex electronics require global supply chains impossible to maintain. Colonies would progressively simplify their technology, replacing sophisticated systems with robust mechanical alternatives. Within centuries, high technology would be gone, replaced by maintainable steam-age equipment. The trajectory would be steadily downward, controlled technological regression. Medical care would stabilize at a basic level. Surgery, wound care, and simple medications could continue. But cancer treatment, organ transplants, and other advanced procedures would disappear. Life expectancy would drop dramatically. Infant mortality would rise. Women would face childbirth without modern obstetrics. The population would need higher birth rates to offset increased deaths. Genetic drift in small populations would be significant. Even with careful management, harmful mutations would accumulate. Isolated colonies would diverge genetically. After thousands of years, different colonies might be subspecies. This assumes no genetic engineering. With that technology, colonies could maintain or even improve their genetic health indefinitely. The purpose problem would be existential. Why survive in a dead world with no future? Religious communities might fare better, finding meaning in survival itself. Scientific communities might be motivated by preserving knowledge. But many would question whether existence in permanent darkness, eating insects and recycled waste, was worth preserving. Resource conflicts would be inevitable. If one colony's reactor failed, would neighbors share power or protect their own? Wars over geothermal sites or functional technology would be likely. The same tribalism that helped humans survive prehistory would re-emerge. Cooperation would compete with competition for determining who survived longest in the darkness. Without the sun's light and heat, Earth would essentially become a rogue planet, a world drifting through space untethered from any star. While still technically orbiting our dead sun's mass, Earth would share more characteristics with the hypothesized rogue planets floating freely through interstellar space than with the living worlds orbiting active stars. Rogue planets are thought to be common in our galaxy. Gravitational microlensing surveys suggest there might be billions of them, outnumbering stars. These worlds were ejected from their birth systems by gravitational interactions, or formed independently from collapsing gas clouds. They drift through the darkness, their surfaces frozen, their atmospheres possibly collapsed into ice. Earth would join their ranks, though still gravitationally bound to a dead star. The surface conditions on Earth would match theoretical models of rogue planets. Temperature would stabilize around -400 degrees Fahrenheit, -240 degrees Celsius, just 33 degrees above absolute zero. At this temperature, most atmospheric gases would freeze solid. Nitrogen snow would fall until the partial pressure dropped too low. Oxygen would liquefy, then freeze. Only helium and hydrogen would remain gaseous, and Earth has too little of these to matter. Interestingly, Earth's core would keep the planet alive far longer than its surface. Radioactive decay of uranium, thorium, and potassium in the mantle generates about 47 terawatts of heat. This would continue for billions of years, gradually declining as isotopes decay. The core would remain molten, maintaining Earth's magnetic field. Plate tectonics might continue at a greatly reduced rate. Volcanism would persist, though less frequently. The magnetic field would be Earth's lasting signature in space. It would continue deflecting cosmic rays and solar wind from other stars we pass. Aurora displays would cease, they require solar particles, but the magnetosphere would endure. Any advanced alien civilization detecting Earth would note this magnetic field as unusual for a frozen world, possibly indicating a large, differentiated planet with a liquid core. Atmospheric escape would be minimal at such low temperatures. The molecules would be moving too slowly to reach escape velocity. Earth would retain its atmosphere as a frozen shell on the surface, a layer of nitrogen and oxygen ice perhaps meters thick. If Earth somehow warmed again millions of years hence, this atmosphere could theoretically revaporize, though its composition would be altered by chemical reactions during the freeze. Earth's orbit would remain stable for eons. Without the sun's radiation pressure and solar wind, orbital decay effects would disappear. The moon would continue orbiting, slowly spiraling away as it does now through tidal interactions. In about 50 billion years, the moon would reach its maximum distance, then begin falling back as tidal forces reverse. But this assumes Earth and Moon survive that long. Interestingly, Earth might be more detectable as a rogue planet than as a living world. The contrast between its warm core and frozen surface would create a distinctive infrared signature. The volcanic activity would occasionally breach the ice, creating temporary hotspots visible to sensitive telescopes. Advanced civilizations conducting surveys might notice Earth as an anomalous rogue planet with unusual geological activity. The long-term trajectory would be gradual cooling over billions of years. Models suggest the core would solidify in about 91 billion years without the sun. But as a rogue planet, without solar tidal heating, this might happen slightly faster. Once the core solidified, the magnetic field would disappear. Plate tectonics would cease. Earth would become truly dead, inside and out. Collision risks would change dramatically. Currently, the sun's gravity deflects many objects that might hit Earth. As a rogue planet, Earth would be more vulnerable to impacts from interstellar objects. Over millions of years, Earth might accumulate a coating of interstellar dust and occasional impacts from other rogues. These collisions would be rare but catastrophic when they occurred. If Earth passed close to another star system, it might be temporarily captured into a distant orbit. The frozen atmosphere might partially thaw. But any captured orbit would likely be unstable over geological time. Earth would eventually be ejected again, returning to rogue status. These brief warm periods would be too short for life to re-emerge. The philosophical implications are profound. Earth would become proof that planets can outlive their stars, carrying the geological and chemical evidence of their living past through the cosmos for eons. Our frozen world would be a message in a bottle, drifting through space, containing the complete fossil record of a biosphere that once thrived. The thought experiment of a suddenly dark sun teaches us profound lessons about life's requirements and the extraordinary circumstances that allow Earth to harbor biology. These insights extend beyond our planet, informing our search for life elsewhere and our understanding of habitability throughout the cosmos. The absolute dependence on stellar energy reveals how life as we know it is fundamentally a system for capturing and utilizing starlight. Photosynthesis directly harvests photons. All other life either eats photosynthesizers or eats things that do. Even chemosynthetic organisms at hydrothermal vents rely on chemical gradients ultimately created by stellar-powered geological processes. Stars aren't just lights in the sky. They're the engines that drive biology. This dependence suggests that most life in the universe probably clusters around stars. The vast spaces between stars, containing the majority of galactic volume, are likely biological deserts. Life might exist on rogue planets with internal heat sources, but it would be simple, limited, and rare compared to stellar systems. The habitable zone concept, the distance from a star where liquid water can exist, gains new significance when we see how quickly Earth would freeze without constant heating. The rapid collapse of Earth's biosphere without sunlight demonstrates life's fragility. Despite 3.8 billion years of evolution, despite extraordinary adaptations to extreme environments, despite the tenacity of life in every niche, the whole system depends on continuous energy input. This suggests that life elsewhere might be equally vulnerable to stellar variations. Stars that vary in output, even slightly, might prevent complex life from establishing. The survival of hydrothermal vent ecosystems shows that life doesn't absolutely require sunlight, just energy gradients. This expands possibilities for life in the universe. Moons like Europa and Enceladus, with subsurface oceans heated by tidal flexing, might harbor life despite being far from the sun. Rogue planets with radioactive cores might maintain deep biospheres. Life might be possible in more places than we assumed, just not the complex surface life we're familiar with. The experiment reveals the importance of atmospheric retention. Earth's atmosphere wouldn't escape immediately, but it would freeze out. Smaller worlds with weaker gravity might lose atmospheres entirely when cooling. This suggests that planet size matters for habitability, not just for holding atmosphere, but for maintaining internal heat that prevents atmospheric collapse. Mars, already small and cold, would fare even worse than Earth. Time emerges as a critical factor. Earth's biosphere collapses in weeks without sunlight, but technological civilization might persist for years. This suggests that the window for detecting living worlds versus recently dead ones might be narrow. Biosignatures like atmospheric oxygen can persist long after life dies. We might detect zombie planets, worlds with biosignatures but no active biology. The role of water as a thermal buffer gains new appreciation. Ocean worlds might maintain habitable conditions longer than dry planets during stellar crises. This suggests that planets with more water than Earth might be more resilient to stellar variations. The water worlds we once thought too dilute for life might actually be biology's best insurance against stellar instability. Energy storage emerges as evolution's unsolved problem. Despite billions of years of evolution, no organism has developed the ability to store enough energy to survive extended darkness. Hibernation and dormancy are temporary solutions. This suggests that life elsewhere probably faces similar constraints. Biology operates on just-in-time energy delivery, making it vulnerable to supply interruptions. The thought experiment highlights the importance of stellar longevity. Stars much more massive than our Sun burn out in millions rather than billions of years. This might not be enough time for complex life to evolve. Red dwarfs, which can shine for trillions of years, might be better suited for life despite being dimmer. Stellar stability over geological time might be more important than total energy output. The interconnectedness revealed by ecosystem collapse shows that complex biospheres require diverse, interdependent communities. Single-species ecosystems are vulnerable. This suggests that the evolution of complex life elsewhere would require similar diversity. Planets with limited environments might never develop beyond simple organisms. The combinatorial explosion of species interactions might be necessary for biological complexity. Finally, the experiment demonstrates that intelligence and technology provide only limited protection against cosmic catastrophes. Despite all our capabilities, humanity couldn't survive long without the sun. This suggests that even advanced civilizations remain vulnerable to stellar events. The great filter that prevents the galaxy from being overrun with intelligent life might simply be the rarity of stable stars that shine steadily for billions of years. After exploring the impossible scenario of instant solar death, we return to reality with profound appreciation for our star's actual stability. The sun will not suddenly go dark. Instead, It will continue its steady fusion burning for approximately 5 billion more years, following a well-understood stellar evolution path that gives life enormous time to adapt or escape. The Sun currently fuses 600 million tons of hydrogen into helium every second, converting 4 million tons of matter directly into energy via Einstein's E equals mc squared. This process has continued steadily for 4.6 billion years and will continue for billions more. The Sun is middle-aged, having consumed about half its hydrogen fuel. But stellar evolution isn't linear. The Sun is actually growing brighter over time, increasing luminosity by about 1% every 100 million years. This gradual brightening will eventually trigger Earth's real apocalypse, though far gentler than instant darkness. In approximately 1 billion years, the Sun will be 10% brighter than today. This extra heat will trigger a runaway greenhouse effect. Oceans will evaporate. The atmosphere will escape to space. Earth will become like Venus, a scorched, lifeless world. But this process will take millions of years, not minutes. The Sun's main sequence lifetime depends on the balance between gravity pulling inward and fusion pressure pushing outward. This balance is self-regulating. If fusion increases, the core expands and cools, reducing reaction rates. If fusion decreases, gravity compresses the core, increasing temperature and reaction rates. This feedback loop has maintained stability for billions of years and will continue doing so. Eventually, the Sun will exhaust hydrogen in its core. In about 5 billion years, core fusion will cease. But the Sun won't immediately die. Instead, it will begin fusing hydrogen in a shell around the inert helium core. This shell burning is less stable than core fusion. The Sun will begin expanding, becoming a red giant star. Its surface will cool, but its size will increase dramatically, possibly engulfing Mercury and Venus. During the red giant phase, the Sun will be vastly larger, but actually cooler at its surface. Earth might survive the expansion, orbiting within the Sun's outer atmosphere, but the planet would be sterilized by intense radiation long before. The red giant phase will last about 1 billion years, during which the Sun will lose significant mass through stellar wind, causing planetary orbits to expand. The Sun will eventually begin fusing helium into carbon in its core, a process called the helium flash. This will stabilize the star temporarily in what's called the horizontal branch phase. But helium burning is much faster than hydrogen burning. Within 100 million years, the helium will be exhausted. The Sun lacks sufficient mass to fuse carbon, so this marks the end of fusion energy generation. Without fusion pressure, gravity will compress the Sun's core into a white dwarf, a city-sized object containing half the Sun's mass. The outer layers will be expelled as a planetary nebula, a beautiful shell of glowing gas expanding into space. The white dwarf will be incredibly hot initially, but will have no energy source. It will slowly cool over trillions of years, eventually becoming a black dwarf, a cold, dark crystal in space. This gentle death, spread over billions of years, gives life options that sudden darkness wouldn't. Intelligent species could migrate to other star systems. They could build artificial habitats powered by fusion. They could even potentially extend their star's life through stellar engineering, removing mass to reduce fusion rates or adding fresh hydrogen fuel. The gradual timeline makes survival possible. Understanding stellar evolution has profound implications for finding life elsewhere. Stars more massive than the Sun evolve faster, giving life less time to develop. Stars less massive evolve slower, but might be too dim for complex life. The Sun appears to be in a sweet spot, massive enough to provide abundant energy, stable enough to shine steadily for billions of years, but not so massive that it burns out quickly. The Sun's actual future confirms Earth's temporary nature as a habitable world. We exist in a narrow window of cosmic time when conditions are just right. Too early, and Earth was molten rock bombarded by asteroids. Too late, and it will be a scorched desert. This cosmic perspective makes our moment precious. We live in the brief epoch when Earth can support complex life. The contrast with our thought experiment is stark. Instead of minutes to react to sudden darkness, life has billions of years to adapt to gradual changes. Instead of freezing, Earth will burn. Instead of sudden cessation, the sun will transform through multiple stages. Reality is both more mundane and more magnificent than our impossible scenario. A slow cosmic evolution rather than instant catastrophe, giving life the gift of time.